Bismillahirrahmanirrahim. In our today's lecture, we'll be talking about particle size. So, initially, different particle size we've already discussed in our class. So, I will jump straight to the particle size distribution, or we can simply call that as particle size analysis. So, we have learned in our class already that particle size analysis is done in two parts. If the particle size is ranging or is greater than 0.075 millimeter, then we go for a sieve analysis, and if the particle sizes are lesser than 0.075 millimeter, then we have to do a hydrometer analysis. And in general, we know that particle sizes that are greater than 0.075 millimeter, that include sands, that include gravels, all right, and obviously cobbles and boulders. And particles that are smaller than 0.075 millimeter, that are silts and clays. So in general, we can say that silts and clays are done for particle size analysis by using hydrometer analysis, whereas soils other than silts and clays, that are sand, gravels, boulders and cobbles, all of them are classified based on particle size analysis using the sieve analysis, or we also call that as a mechanical analysis method. So talking about sieve analysis, let's talk about sieves, how they look like. So this is a typical sieve. You see, these are some typical sieve examples. So they have a raised collar, all right, they are circular in shape, and at the base of the shape we have opening, and those opening sizes are measured. Okay, so this is a typical size. If you can see at this this figure here, you see that the opening size has been measured. It is 3 inches. So the size of opening is 3 inches. Okay, so this is a figurative diagram of the plan view, and this is a elevation view of these sieves. So while we are talking about sieves, so there are different sieves, and sieves are classified based on sieve number. So if we look on our right side here, you see here it is mentioned sieve number 3. So how is it called sieve number 3? It is based on the number of openings per linear inch. So if you look at the figure here, you see this has been marked as 1 inch. So in 1 inch there are 3 openings, right? So 1, 2 and 3. So that's why we call that as a sieve number. So if there are 3 openings in a linear inch, that we call is as a sieve number 3. And similarly, if a sieve has 4 openings in a linear inch, then we call that as a sieve number 4. So there is a table that is provided here. Sorry for the messy board, but I've already taught the class, so that's why while discussion the markings have been made. So, this is the table here. You see we have first sieve designation and then the opening size. Now opening size is written here in millimeter, and it's important to note here that sieve number 4, all right, so it is 4.75 millimeter, that's the opening size. And then this is how we move down. Then we have sieve number 100, 200, 40. There are a lot many sieve, only few of them are mentioned here. You can find all the sieve numbers, their opening sizes from the lab manual. There is a whole list, and also in your books. So one important point that I wanted to highlight here, that up to sieve number 4, all right, that means there are 4 openings in a linear inch, all right. Any size smaller than that is mentioned with the sieve number. That this is sieve number 8, so that means there are 8 openings in a linear inch. Sieve number 16, so that means there are 16 openings in a linear inch, and so on. Anything that is larger than that, we designate it directly with size in opening. Okay, so this is 4.75 inches, sorry, 4.75 millimeter. This is our size or opening size for sieve number 4, and this, when it says 3 by 8 inches, so it is directly telling us the opening size. I'll repeat again. Sieve number 4 means there are 4 openings in the linear inch, all right. That means if this is an inch, there will be 4 openings in it. 1, 2, 3 and 4. Now obviously there will be same size. Sorry for my bad drawing. So this is 1 inch, so that means there's a 1, 2, 3, 4. So that means this is the sieve number 4, all right. That has also been shown here, that this is sieve number 4 here. And any opening that is larger than 4.75 millimeter is generally designated with the number. So that means if sieve number 3 by 8 inches means that any opening in the sieve will be having a size of 3 by 8 inches in this direction or in this direction. It works in both ways. Similarly, in sieve number 4, there will be 4 openings in a horizontal linear range. So is it clear? A sieve number 2 inches designation sieve means that the opening size is 2 inches and that is the clear opening. Alright. So these were the sieve numbers. Okay. So now how we while talking with the sieve numbers, there are 2 important sieves that we require that you remember the opening size and the sieve number as well. Sieve number 4 here, that is having an opening size of 4.75 millimeter, and sieve number 200 here, that is having an opening size of 0.075 millimeter. Why are they important? That anything that is larger than 4.75 millimeter or sieve number 4 is classified as gravel. There are obviously cobbles and boulders also, but for our Geotech 1 course, we only stick ourselves to gravel, sands, and silts and clays. So that's why I'm saying it, that above sieve number 4 or 4.75 millimeter, any particle that is larger than that is gravel. So that means if I take a sample and I place it on sieve number 4 and I sieve it and I shake it, all the material that is smaller than 4.75 millimeter will pass, and anything retained on top of sieve number 4 will be the gravel. Similarly, why sieve number 200 is important? Because anything that passes sieve number 200 or anything that is smaller than 0.075 millimeter, that is fine grained soil, or we call that silts and clays, and anything retained on top is either sand or gravel. Now, sands will be having size between sieve number 4 and sieve number 200. Silts and clays will be having sizes smaller than sieve number 200, and gravels will be having a size larger than sieve number 4. So please, it is requested that you remember by heart that opening size of 4 is 4.75 millimeter and sieve number 200 is 0.075, and we know that they are the distinguishing line between the coarse grained and fine grained soil, especially sieve number 200. Okay, and we know that gravel will be having a size larger than sieve number 4. Gravel also comes in coarse grained soils. So now we are familiar with the sieve numbers as well as the important sieve numbers. All right. Now we see how we carry out the test. Now what we will do, we will take sieves depending on the project that we are doing. We will arrange the sieves that fit our requirement in a sequential order. Now sequence is such that the largest opening comes on the top and the smallest opening comes at the bottom. All right, because we know that if the particle size is smaller, so they will pass from the larger sieve and they keep on retaining on whichever sieve is having a smaller size than the particle size. Okay, so for example, this is a picture from our lab that they have arranged the sieve, and while we arrange the sieve, we call that as a sieve nest. Okay, and we have placed, you see this green machine here, this is called a sieve shaker. So we will arrange the sieves and the arrangement is called as nest of sieves, and the arrangement is such that the largest opening comes on the top and the smallest opening comes at the bottom. Okay, and we will place the sample on the top. Okay, and then we also place a lid on the top. There is a lid generally on the top. Okay, so that no dust or extra particles moves away while we are shaking the soil. So after placing after arranging the sieves in order, place the sample on the top, and we obviously take a known amount of sample. For example, we can take 500 grams of soil sample, and then we turn on the sieve shaker, shake it for like 8 to 10 minutes, and after that, once you are done with the sieve shaking, what you will do, you will take each sieve and then empty the content on the sieves, retain on the material retained on each sieve. Okay, so what will I do? For instance, this was, let's say, sieve number 4. So I took the sieve number 4 to the weighing balance here. Okay, so either you can pre-weight the sieves and then add the total weight to find out the weight of the sample retained, or either you can empty the retained content on a piece of paper and then weight that weight that is coming, and we note that as weight retained. So you get the point. After sieving all the samples, we have to empty all the sample retained on the sieves and we weight them. Okay, now a question might come, what happens if a sample gets stuck, if a soil particle gets stuck in the sieve? So we do not push it, because if it was smaller than the opening size, then it would have automatically passed on it on. This means the particle is a little larger than the opening size, so that's why we press it from the back side and we count the stuck particle in the weight retained. Okay, now moving towards the calculation process. So what we are doing here, these are the sieve numbers 4, 10, 40, 100 and 200, and we will write the sieve sizes here in millimeters, and then we will write the weight retained. So after calculating from the weighing balance, just write the weight retained in front of the particular sieve. Okay. There is a nice table here regarding the calculations. I'll just look for that table. Yep, here it is. So this is the table for calculation of sieve analysis. So you see here on the top we have the sieve number, all right, and we have the particular sizes for the sieves, okay, and then weight retained. So for example, we did a test, we took 500 grams of a soil, and these were the soil's weight retained on each of the sieves. After writing these 1, 2 and third column, we write the fourth column. For this fourth column is percentage weight retained, and how we calculate it, it is the weight retained on a particular sieve divided by the total weight. All right, so you see here total weight was 500 grams. So in the sieve 3 by 4 inches, you see 0 weight, so that is percentage weight rated 0, 0, 0, 0, 0. Now we come to this sieve number 10. On sieve number 10, weight retained was 0.3 gram. So what we did, we divided 0.3 with 500. Let me zoom that up for you. So 0.3 divided by 500 multiplied by 100, so it gave us 0.06%. Similarly, weight retained on this next sieve number 40 was 75.754. Sorry, 75.74. So we will divide that with 500, multiply that with 100, so it will give us 15.148. So similarly, we will find out percentage weight retained on each sieve. After you're done with this column, we write another column that is called as cumulative percentage weight retained. What is this? It is simply addition of the previous value. So this is 0, so the first value comes as it is from the previous column, okay, because there is no previous value to it, so that's why 0 will come here. And then again this is 0, 0 comes here, 0 comes here. And now in this column we have the first value of percentage weight retained, so we'll write 0.06 here, okay. And then next value in the lower row, in this lower row, what you will do, 0.06 add 15.148, and it will give us a total sum of 15.21. So this is the so what we have done here in this column, that we have added all the weights retained so far, percentage weight retained so far. In the next column, sorry, in the next row, this one, when I'm putting the star, so it will be addition of, sorry, there will be addition of all these three values, okay, that will come here. So that is 80.26. And lastly, in the last row, it will be addition of all these four values here, and we write it here. Okay, so we are adding up all the percentage weight retained. And lastly, the last column is percentage passing, and how we get it, it is simply 100 minus percentage cumulative retained. Okay, so this is 100 because this is 0, 0, 0, and here it is 100 minus 0.06. So that is 99.9, and next will be 100 minus 515.21. It will give us 84.8, and then 100 minus 80.26. It will give us 19.7%. So this is all the percentage passing. So this is how we do the calculation for sieve analysis. Now, out of this table, there are two important columns that we need to note. The first one is sieve size, and then is the percentage passing. Now we plot the graph, okay, for the particle size distribution. Now the graph is very important. The graph that we use is called as a semi-log plot, and we have already discussed that in the class. In a semi-log plot, one axis is log scale and the other axis is arithmetic scale. So the percentage passing scale, that is y-axis, is the arithmetic scale, and the percentage and the particle size is millimeter, that is the log scale. Okay. And one important thing is that this scale is reversed. This is very, very important to remember. A lot of students forget that generally what we have is that we have smaller value on the left and we have the larger value on the right. But this is reverse in our case. Okay, we have the largest value on the left and we have the smallest value on the right. So that actually, if it was a proper scale, so it should have been moved in this way. But in reality, how the scale works is that I'll try to draw it again here. This is the actual scale. So we have percentage passing, because it is arithmetic scale, so that means all the distances are equal. And this one here is reverse, so we have largest value 1000 and we have smallest value 0.01, and then 0.1, 1, 10 and 100. I'll not repeat the detail of the arithmetic scale because we've already discussed in our class that how a log scale is different from an arithmetic scale, but important to remember that this scale is reversed and we call that as a semi-log plot. All right, and we have already discussed in our class that how to read readings from the log plot, from a semi-log plot. Okay, all right, so let me get back just a minute. This is the plotted scale for the table that we just saw for the calculation. So this is the plot of the same values. Okay, so you see again that on the left side we have percentage weight retained, sorry, percentage passing, and that is an arithmetic scale. You see here how all these values are equal distances, and on x-axis we have a log scale and the size is decreasing from left to right. And two important line, blue line, are marked here. They are indicating sieve number 200 because we know that its size is 0.075 millimeter, and sieve number 4 here, that was having a size of 4.75 millimeter. We know that they're important because anything that is larger than 4 is supposed to be gravel, and anything smaller than 200 is supposed to be silts and clays. So just to check, just to have a quick glance how to read this scale here, we see that because we have marked 0.075 here, so you see here this is 0.01, this is 0.02, 3, 4, 5, 6 and 7, this is 0.07. So you see here this blue line, and the next one is 0.08. So the blue line has marked in between, so that's how we read 0.075. Okay, so this is a typical chart. There are certain values we like to read from the chart. Okay, for instance, there is this one thing that is called as D10, or we called it as an effective size or effective diameter. So how do we find it? We will simply go to the percentage passing, we look for 10, we move straight, hit the graph and where the graph hits, move vertically downward. Okay, let me sharpen this up. Okay, I'll just move it a little bit so things are more cleared here. Let me see if I can zoom it up. So what I have done so far, I have simply looked at the percentage passing, that is 10%. I moved straight in a horizontal line and I hit the graph, and then where the graph hits, we move vertically downward. So this value here, this value in millimeters will be D10, that is effective size. Similarly, D30, so I look for 30% passing, I'll go straight forward, hit the chart, and where the chart hits, I'll move straight downward. Now if you can read it out, this is 0.1, this is 0.2, so we are on this side, so approximately I can say that D30 for this soil is, let's say, 0.18. all right, and then another important thing is to remember is D60. So go for 60% passing, go vertically downward and hit the chart. So this is 0.1 and this is 0.3, so that means D60 for the soil is 0.3. all right, so this is how we read the chart. And now you see why these three sizes are important. So there are two coefficients. First one is called as coefficient of uniformity, and then second one is called as coefficient of curvature. The formula for coefficient of uniformity is this, that D60 over D10, and coefficient of curvature is D30 square over D60 into D10. And we will see in a minute that why we need to find them out and why they are important. Before talking about them in detail, about coefficient of uniformity and coefficient of curvature, I will just go back to the sieve analysis and we will have a little more discussion on the same chart. All right, so from the chart, while we have a chart now, this is a very, very important chart. We also called as PSD, or particle size distribution curve. Why is it important? By looking at it, we can tell the amount of percentages of each soil. For example, you see here we know that anything that is smaller than sieve number 200 is called as silts and clays. And if I mark this line here, you see here that this is almost, let's say, 5%. So that means in our sample we only have 5% silts and clays. Okay, and then we have to see that amount of gravel. So I'll go to sieve number 4 and I look here. So this is 100% passing. So that means there is no particle that is larger than gravel. All right, and our soil is lying in between is sand. So that means if 5% is clay, so that means sand for our soil is 95%. Okay. All right. So moving forward, the shape of the graph also tells us a lot about the soil behavior, that how the soil will behave once it is loaded and whenever we are using soil in different conditions. Okay. So let me zoom it out. All right, so now if you look at the chart here, okay, hold on, I'm sorry, it's a little bit, my RAM is running low, so that's why I have a slower output for my laptop. All right, so as we were talking that the shape of the sieve analysis chart can tell us a lot. So typically there are three types of soil that we can differentiate based on the shape of the sieve PSD or the particle size distribution curve. First one looks like this. You see it's almost a flatter curve and it spreads from all the size from 0.001 up to 1000. All right, so it's having almost all particle sizes available. So such type of soil is called as a well graded soil. The second type of soil can be looking like this. It's almost vertical, all right, and we call that as a uniformly graded soil. All right, so you see here this soil has only these limited particle sizes only. There are no larger particles and there are no smaller particles. So that's called a uniformly graded. And lastly, third type could be starting on like a well graded soil, but then there is a gap in the soil. We can mark it with a dotted line. So that means there is a certain portion of particle that is missing. So such type of soil is called as a gap graded soil. All right, so repeating again, if our soil has almost all the particle sizes, then we call it as a well graded soil, and it will be indicated by the curve that is shown in the red, that is spread throughout the graph. It is covering all the particle sizes. Then we have a uniformly graded soil that has only one type of soil particles based on the sizes. There is only one size present and there's no larger particle, no smaller particle. And lastly, we have a gap graded soil where we have larger particles and we have smaller particles, but the intermediate size are missing. So that such soil is called as gap graded. Now poorly graded and gap graded soil are commonly called as uniformly graded soil, and a gap graded soils are commonly called as a poorly graded soil. Okay, so if someone says it's a poorly graded soil, so it can be a gap graded, it can be a uniformly graded, and the other type is well graded soil. Now well graded soil is the soil that we need for all engineering purposes, okay, because that is the best soil that we need. It carries loads very good, it behaves in a very good engineering manner. So all of us want a well graded soil at our sites. And while you can have an estimate by looking at the particle size distribution curve, there are certain checks that if you can apply to the PSD or the particle size distribution curve, you can be sure that if it is well graded or not. So here's the criteria here. If we are dealing with gravels, then for gravels, CC should be between 1 to 3 and CU should be greater than 4. That means coefficient uniformity should be greater than 4 and coefficient curvature should be between 1 to 3. Similarly, if you are dealing with sands here, then to make sure that the soil is well graded, we have to check that CC or the coefficient curvature of that soil or that sand should be between 1 to 3 and coefficient uniformity should be greater than 6. If either of the criteria is not satisfied, that means either C is greater than 4, 3 or less than 1, or Cu is less than 6 or less than 4. If any of the criteria is not satisfied, we call that soil as a poorly graded soil. Alright, so at sites we will always prefer the well-graded soil. Now, one reason that I could explain that why we need a well-graded soil, because we know that well-graded soil contains all sizes of particles. Okay, so if we see that there are larger size particles, so there will be void spaces in between. So for a well-graded soil, these small spaces will be covered by these smaller particles. All right, so load carrying capacity will be very good. The void spaces will be small because all the void spaces will be covered by the smaller size particles. So if there is a load transfer set, so they can easily move from grain to grain contact. All right, so that's why we prefer well-graded soil, because all the void spaces will be most probably filled with the smaller size particles. That does not happen in a gap-graded soil or a uniformly graded soil, because there will be larger void spaces between them. All right, so that was all. That pretty much covers everything related to sieve analysis. All right, now we move to the second type of the particle size analysis procedure, that is reserved for the particle sizes that are smaller than 0.075 millimeter. All right, or we call them as the fine grained soils. So we have already seen that we use hydrometer to do that type of analysis. All right, so in a hydrometer analysis, the apparatus that we use is called as the hydrometer, and the designation is ASTM 152H. All right, and this is how a hydrometer looks like. This is a hydrometer looks like. Okay, let me move to the exact point. So the designation number is apparatus number is ASTM 152H. So what we basically do, the originally hydrometers are used to find out the specific gravity of a solution. If you put them inside a solution, so they will directly tell you the specific gravity of that solution. Now, calculations have been made, all right, by some scientists, all right, people who work in geotechnical engineering. They converted all this specific gravity calculation into our requirement, and we know that to plot a chart we need two things. To plot a particle size distribution chart, we need the percentage passing, as well as we need the particle sizes. Okay, so this same hydrometer analysis that is used for specific gravity solutions has been calculated in such a way that it will give us both values. It will give us the particle size distribution, that will give us the particle sizes, as well as it will give us the percentage passing of that solution. All right, so we have already seen that hydrometer is done for particle sizes that are smaller than 0.075 millimeter or C number 200. Another important thing to remember is that we only do hydrometer analysis if our sample contains larger than 12% of the percentage passing C number 200. If it is smaller, then we might skip the hydrometer test and we only stay to the sieve analysis only. Okay. Now, hydrometer analysis is based on Stokes' law, and that has been mentioned here, that velocity of any particle that we call as terminal velocity, that is falling through a fluid, all right, of having the consistency of mu, all right, that is absolute viscosity of water, all right, is equal to gamma s minus gamma w over 18 mu into d square, where v is the terminal velocity, gamma s is the unit weight of the solid particle of soil that is falling through the liquid, and we are assuming that liquid is water, and gamma w is the unit weight of the liquid or water, d is the diameter of the particle that is falling through the liquid, and mu is the absolute viscosity of water. So if I draw it, so you can imagine that there is one soil particle having a diameter d, and it is falling through a liquid that is water, and it is achieving a velocity that we call as v, or the terminal velocity. So you can imagine that there is this liquid falling, all right, d is the diameter, gamma s is the unit weight of the soil particle, and gamma w is the unit weight of the liquid in which the particle is falling. Okay, so this is the Stokes' law. and the equation of the Stokes law is given here. So that equation has been rearranged, and by calculation we can find out that the particle size, or d, can be found out by calculating and putting values and finding out the formula, that is 18 mu over gamma s minus gamma w over under root L over T. And how we got L over T? We know that V is equal to length per unit time, all right, that is distance covered per unit time, that is velocity, all right. So we have this equation, and this can be written as K. So simply the equation to find out the particle diameter is K under root L over T, all right. Now the formula of L has been calculated to be 16.3 minus 0.146 into R. And what is R? R is the hydrometer reading that is corrected for meniscus only, all right. Now what is R? If we look at the picture here on the top, so once we insert, you see what we will do, we will simply, okay, first I'll have a little go about the procedure, then I'll come back to the situation here. Okay, I'll cover a little bit, actually should be covered in lab, but because we haven't done the lab for hydrometer analysis, so that's why I have to go through a little bit of the detail about the lab procedure, that how we do a hydrometer analysis. So what we will require, we will be requiring ASTM 52H hydrometer. We require 3 suspension jars, all right, that is empty cylinders having a volume of 1000 ml, all right. So I'll draw them here. These are the empty cylinders. So what we do is that we fill with one cylinder up to its capacity with water, and all of them are 1000 ml, okay. And in the next cylinder, what we do, we add water, and then we add the calcium oxalate or whatever dispersing agent you are going to use, or I can simply write here as dispersing agent. All right, so we will use we will see in detail that what dispersing agent and in what ratio we are going to use in our lab class. But for now, you should know that one cylinder contains only water, one cylinder contains water plus the dispersing agent, and the last cylinder that contains water, that contains the dispersing agent, and that contains the soil. Now the soil is generally is 50 gram soil that we take, and this is an oven dried soil. Okay, remember that we require oven dried soil, that is 50 gram. So that comes in the last jar here, and we also call that as a sedimentation jar. So what is the procedure is that, first of all, we have to ensure certain corrections. There are certain corrections that are needed to be applied before we carry out the test. So first correction is called as the meniscus correction. All right, and how we achieve it? Meniscus correction, what will I do? I will simply place the hydrometer, this is the hydrometer, inside the jar that only contains water, and whatever reading it is showing me, okay, so the reading actually, if I let me first draw hydrometer in little detail here. Okay, just a minute. So a hydrometer has a stem. So hydrometer, I'll draw it a little bit clear. This is the hydrometer. It has a stem on the top, and then we have a bulb at the bottom. Now there are steel fillings here. These ensure that the while the hydrometer is suspended in water, it remains vertical. Okay. So there are readings on the stem. That is a graduated stem. Okay. This starts from maybe -5, 0, 5, 10, 15, and so on. All right. So what you are in the first step, what you're going to do is that we will put this hydrometer inside the jar that only contains water, and we'll simply read off the reading of the jar. Okay. If it is 0, then meniscus correction is 0. If it is 1, then the meniscus correction is 1. All right. So this is the first correction that we need to know. Then in the second step, what we are going to do is that we will place this same hydrometer in the second jar that is containing the water as well as the dispersing agent. Now we will note the reading of the hydrometer. This time the reading note is called as the 0 correction. Okay, whatever reading we are getting, we note that reading as a 0 correction. And lastly, we will note the temperature of the water. All right, note the temperature, and we apply the third correction, that is called as temperature correction. And if it is different from 25 degrees C, then we have to apply a correction. If the temperature of water is 25, then we do not apply any temperature correction. But if it is more or less than 25, then the temperature correction can be positive or negative depending on the temperature. So these are the three readings. These are the three corrections that we need to know ahead before we carry on the test. All right. So coming back, so we just learned that R is the reading of the hydrometer with meniscus correction only. So that means, how will I simply find out the diameter of the particle inside the suspension is that I will simply just a minute again. So this is how we will find out the diameter of a particle inside the soil suspension by this formula: d is equal to k under root L over T, and we learned that L is equal to 16.3 minus 0.6164 R, where R is hydrometer reading that is corrected for meniscus only. So that means we will insert the hydrometer inside the sedimentation jar, the jar that contains water, dispersing agent as well as the soil. In that we will note the hydrometer reading, we only correct it for meniscus, and then we place that value here. Okay, so simply you can plug in the R value, find out K and L and T. Now what is T? Now the procedure is that what we do is, after noting the corrections, we will shake our sedimentation jar before starting the test. Okay, we'll place a rubber stopper on the top, and the sedimentation jar that contains the three components: water, dispersing agent as well as the soil, oven dried soil, we will shake all the contents very well and then place the jar on a level surface. And as soon as you do that, you will insert a hydrometer very carefully. All right, and then as soon as your hydrometer is placed inside the sedimentation jar, you turn on the stopwatch. All right, and what you do is that with time you will keep on noting the reading. So that means, and what we do is that after inserting the hydrometer, what we note reading as 0 minute, 1, 2, 3, 4 and so on. So this is time in minute, and this is the reading of the hydrometer. So because what will happen, that hydrometer reading will keep on changing with time. So for 1 minute, 2 minute, 3 minute, 4 minute, you will note that reading. Okay, and in this equation, so that means for every time reading you will have a different value of D. So simply place in the reading of the time, it's 1, then write the corresponding reading of R, obviously with meniscus correction. Okay, and then for the time reading of 2, you will place the second reading against the value of time 2 with the meniscus correction. All right, so this is how we calculate the value of D. And before moving further to the percentage passing, there is a quick review again of the corrections that we need to apply before starting the test. Just a minute. So we have temperature correction. It can be plus and, sorry, please, my bad. The temperature was 20 degrees C. That is our reference temperature, not 25. So please note this correction. So if it is plus or negative, so it will automatically, we have a table where we have the values of temperature correction based on the temperature. And then zero correction is always negative. All right, that is due to the dispersing agent, and meniscus correction is always positive. So the total corrected reading for hydrometer is R actual, that is the reading that you observe with your eye, plus meniscus correction minus zero correction plus minus temperature correction depending on the temperature. Okay, once again, to remind you that the equation of R that we need to find out, L, only includes the hydrometer reading directly that you observe from the eye with meniscus correction only, whereas RC is a different value that contains all the corrections of temperature, meniscus, and the zero correction. All right, now where we are going to use this RC that is including all the corrections, we will use this value to find out the percentage passing, or we also call that as percentage finer. So the formula for that percentage passing or percent finer is written here. You can see that it is equal to A into RC over WS into 100, where A is a correction factor based on the specific gravity. If your specific gravity is 2.6, then we do not need a correction factor, and if it is different from 2.6, then we need to apply a correction factor of A, and we have formula for that available. We can discuss that in the lab, that what is the formula. RC is this corrected reading including all the three corrections, and WS was the weight of the open dried soil, and we remember that we took 50 grams. So this is the table above that is showing all the readings. You see here that we are noting the reading of the hydrometer at these term intervals, and temperature we have also been noted, temperature correction, this is based on the temperature, and this is the actual hydrometer reading that you have noted. So see here, initially hydrometer reading will be large and it keeps on decreasing with time. All right, and then we find out RC that is including all the correction, and this one is the R that is including only the meniscus correction. Okay, so percentage finer, we use this formula to find out the percentage finer, and this R will tell us L, and then we find out L over T, then we find out K. Now K is also based on a table values. We have all these tables available in your lab manuals, and lastly we have D. So based on these two values, that is percentage finer and D, we can plot the particle size distribution curve. So if you remember that in the particle size distribution curve, we have this percentage passing and we have die here, and this was sieve number 200. So with the sieve analysis, we were able to plot graph up to this point, and the values of the soil that are below it will be now found out by the hydrometer, will be plotted here. All right, so remember that the graph here will be plotted by the hydrometer, and the graph here that is larger than sieve number 200 will be based on the sieve analysis calculations. All right, so any questions that are related to the hydrometer analysis will be once again addressed in your lab class as well as in your theory class. Now we move to the second portion. After the particle size analysis, we will discuss the Atterberg limits. So Atterberg limits are very important because they are both of these things, that is the particle size analysis as well as the Atterberg limits, both of them are used for the soil classification. That is the next topic or discussion.